Lab 2, Motion of a Falling Object. Lab 2 involves analyzing the motion of a falling object. Therefore, this lab involves Newton's second law of motion, which is velocity final equals velocity initial plus net force divided by mass times the change in time. But the force will not be zero because the force of gravity and air resistance are both in this system. In this experiment, the object used is a stuffed Winnie the Pooh doll that weighs approximately 0.362874 kilograms. Winnie the Pooh starts with a velocity and position of 0, and the change in time during the experiment is 0.458. To model the effects of the force on the velocity, there will be two models. The first will be just the force of gravity, and the second will be both the force of gravity and drag, or air resistance. In the first model, the net force will equal weight, which is the force of gravity on an object, negative 9.8 newtons, times mass, times the unit vector j hat. In the second model, the net force will equal weight plus the drag force, which is negative b, which is the proportionality constant, times velocity. First, I measured the length at Winnie the Pooh's widest part to be 0.2921 meters. Next, I set the origin to what I thought was the center of the bear. Then, I kept plotting the center per frame. For the first model of the experiment, dealing solely with gravity, I changed the mass to Winnie the Pooh's mass. Then I changed the initial position to 0. And then I changed the initial velocity to 0. And time was 0 as well. I left delta t very small so that you could easily make a comparison between the experiment and the model. I set gravity to 9.8 and j hat to the unit vector of the y-axis. Then, to set up the loop to find the velocity and position, I changed the final time to 0.458 and set the weight equal to the weight formula and set the net force equal to that weight. When we run the model, we see a similar motion to that of the Winnie the Pooh doll. The results show that between 0 seconds and 0.25 seconds, the model underpredicts the velocity. Then, from 0.25 seconds to 0.458 seconds, the model overpredicts the velocity. The model appears to have terminal velocity from 0.18 to 0.3 seconds. For the second model, predicting with both drag and gravity, we set the b constant to 0.53 so that the final velocities in both the experiment and model are equal. For the loop, everything stays the same except we add the line for drag force. Then, we change the net force to equal weight plus drag force. For this model, we added arrows to represent the forces of gravity and drag on the Winnie the Pooh doll as it falls. When we run the model, we see that the yellow arrow, representing gravity, pulls the doll down, and the blue arrow, representing drag, pulls the doll in the opposite direction. In this model, from 0 to 0.35 seconds, the model underpredicts the position, then slightly overpredicts the position from 0.4 to 0.43 seconds. The model appears to have terminal velocity between 0.2 to 0.458 seconds. If the object were to be thrown downward instead of dropped, the terminal velocity would be different because there would be another force on the object. When both the model positions and the experimental position are plotted on the same graph, you can see that both models underpredict the position until 0.2 seconds. Then, from 0.2 to 0.26 seconds, the model of gravity is a good prediction. Then from 0.3 to 0.458 seconds, the model of gravity and drag is a good prediction.